Next is orthogonal vectors. If vector x is not equal to 0 and vector y is not equal to 0, that is x and y are non-zero vectors, then we have also angle between vector x and vector y is pi by 2, then we say that vector x and vector y are orthogonal vectors. Now, necessary and sufficient condition for two non-zero vectors to be perpendicular to each other. That is, let vector x and vector y are two non-zero vectors. That is, vector x perpendicular to vector y. That gives angle between two vectors is pi by 2. That is, cos of angle between x and y is cos of pi by 2. That is, cos of angle between x and y is x dot y over modulus x over modulus y, which is equal to cos pi by 2, that is 0. That gives, as modulus value is not equal to 0, therefore, which implies x dot y is equal to 0. Therefore, if angle between x and y is pi by 2, then x dot y is equal to 0. That is, vectors are orthogonal. So this was a necessary and sufficient condition to prove two vectors to be orthogonal. So if we find dot product of two vectors and it's come out to be 0, then two vectors are orthogonal. Now next is theorem 6.7. If vector x and vector y belongs to R cube and x is non-zero vector and y is non-zero vector and angle between x and y is alpha, then prove that first part x dot y is equal to modulus x into modulus y cos alpha. So first we will prove the first part, that is proof of this is by definition of measure of angle between two vectors, we get alpha is equal to cos inverse x dot y over modulus x into modulus y. So we get cos alpha is equal to modulus x into cos alpha is equal to x dot y over modulus x over modulus y. So by cross multiplication we get x dot y is equal to modulus x modulus y cos alpha. So this can be used in this form also. The next part is modulus of x cross y is equal to modulus x modulus y sin alpha. Now for this we will use Lagrange identity. So proof of this is by Lagrange's identity we have modulus x plus x cross y whole square plus modulus x dot y whole square is equal to modulus x square modulus y square. That is modulus x cross y is equal to modulus value x square into modulus value y square minus x dot y modulus square. So as we done in the first part, using this we get modulus x dot y whole square is equal to modulus x whole square modulus y whole square into cos square alpha. So we will take common modulus x square modulus y square 1 minus cos square alpha. So we get modulus x square modulus y square sin square alpha. So on taking square root we get modulus x cross y is equal to modulus x into modulus y sin alpha. So this is the second result of this theorem. Now the third part is show that vector x is perpendicular to vector x cross y and vector y is perpendicular to vector x cross y. So proof is just like that. It is very simple. That is, we have to prove vector x is orthogonal to this vector y and x cross y is also orthogonal. Let vector x is in component form x1, x2, x3 and y is in component form y1, y2, y3. So now we will find x dot x cross y, that is determinant x1, x2, x3, x1, x2, x3, y1, y2, y3. This is equal to 0 because if two rows are equal in a determinant, then value of determinant is equal to 0. This is a property of determinant. And also vector y dot x cross y is equal to y1, y2, y3, x1, x2, x3, y1, y2, y3 again. As two rows are similar, therefore this is also equal to 0. That is, dot product of two vector is 0. So if dot product of two vector is 0, then we say that these two vectors are orthogonal. Therefore, vector x is perpendicular to vector x cross vector y and vector y is perpendicular to vector x cross vector y. Thus, we can say cross product of vector x cross y is a vector orthogonal to vector x and vector y. Therefore, plus minus x cross y over its magnitude, that is a unit vector. So these both are unit vectors orthogonal to vector x and vector y. So it was all about theorem 6.7.